March 1965, Gus Grissom and John Young go up successfully in the first double-crewed mission for the Gemini program. And the Gemini program is especially important for us to think about. Lots of people may kind of like skip over it. Mercury started the program, Apollo gets us to the moon, but as you'll learn in today's conversation, without Gemini, there would have been no Apollo program. Gemini is critical to being able to prove that we can do certain things that must be done if we're going to actually be able to get man to the moon and then hopefully get him back home successfully as well. Welcome to Rittner High School for today's History in the First Person program, the Gemini Project. Hi everybody, I'm Tim Gore and I'm very happy to welcome you to the home of the Huskies, where today we're going to interact with engineers who are part of making the Gemini program successful. Let's begin by introducing our panel of experts who are with us today. I want to start on my far right with Bob Schepp. Bob, thanks very much for joining us today. Bob, in the infamous 15-second nutshell, what did you get to do with Gemini?
Oh, well, I got to work on some of the strange programs. I worked on the target docking adapter, and no one in the whole world knew this, but we also had a paraglider. We were going to land it on land. And so those are the two main programs, and then I was responsible for the launch operations checkout before we sent them to the Cape for all even-numbered Geminis.
And you're going to get to learn a lot more from Bob about those things. To his left is Dean Purdy. Dean, thanks for being with us today.
Yeah.
Short description of your work on Gemini?
Electrical power and sequential system, and test operations at St. Louis.
Okay. And when you say sequential systems, that means things happening in the right order?
That's correct.
Okay, good.
Yes.
That would always be helpful, I suppose,
Yes.
for the launch to actually occur.
Works better that way.
To my immediate right is Earl Robb. Earl, thanks for joining us today. Your world with Gemini?
Well, I worked on the original design of Gemini, and the work was structural mechanical design. Best part of all of that, I think, was the working with the astronauts and developing items that had to be used for successful EVA. The astronauts.
And by EVA, you mean the extravehicular activity, the spacewalks?
Yes.
That they would do, and that were an essential part of the Gemini program. We're going to get to see some really cool video of spacewalks. To my left is Jerry Roberts. Jerry, thanks for joining us.
Thank you. My specialty was guidance and control, specifically included the guidance computer, the inertial measuring unit, the auxiliary tape unit, the horizon sensor, but whatever was necessary to show the astronaut, it sounds pretty mundane, but to show him which way is down, we always had to point to the center of the Earth to give him a reference. And then as part of the rendezvous and docking, there are small little computer, as small as it was, and it was only 400 or 4K of memory. As small as it was, we actually did all of the calculations for each phase of the mission, including the rendezvous and docking.
And we're going to get to talk about rendezvous and docking quite a bit today. I'm looking forward to that. Norm Beckel is to his left. Norm, thanks very much for being with us. Communication systems?
Communication systems. We had voice communications, so we could talk to the astronauts. We had telemetry, so we knew what was going on, and radar beacons, so we knew where they were at. We had a radar on the front of the vehicle to be able to acquire the Agena, and a lot of antennas on there.
And the Agena is a spacecraft that they were, in essence, practicing rendezvous and docking with as part of their missions. We'll talk about that. And last but certainly not least, Ray Tucker, thanks for being with us today. Ray, electrical ground support?
Electrical ground support, all the cables from the blockhouse through to the spacecraft, checking them all out, making sure every circuit was completely right. If it wasn't right, I was in trouble. But I sure enjoyed it.
And as you're going to learn from Ray, there was a lot of cable coming from the launch site to the blockhouse. It's a different operation than would be true today. We're going to begin by getting some sense just of the time period. Early 1960s, the Mercury program has been successful from 61 to 63. We had 6 manned Mercury missions. Then the Gemini program starts up, and in 65, Grissom and Young go up. So let's talk a little bit about this technology at the time. We got some great pictures we can show you of computers of the middle of the 1960s. Today, of course, my phone does amazing things, and the computer in your classroom does amazing things, but the computers back then were much larger and couldn't do nearly the computations per second or per minute that we're capable of doing today. So as we look at these computer pictures, I'll invite Phoenix and Amelie to join us at the microphone over there, because we're going to get to your questions in just a minute. But I want to go down to Elkins High School, because I think Jack from Texas has a real interesting question for us to get started with. So Jack, I'll turn to you. What's your question?
Where would the U.S. space program be today if today's technology existed around the time of the Gemini project?
So Jack's asking, what would it be like if we had today's technology back then? So let's talk a little bit about the technology you had back then and what you had to work with, and then maybe one of you can choose to speculate a little bit. Jerry, you've already started giggling, so I guess I'll have to...
I'm just thinking of getting rid of my slide rule. That'd be the first thing would happen if we had today's computer. The other thing is that the design and integration time would probably be days as opposed to months. As I've said before, we didn't invent hardly anything back then because we did not have the time to do it. But if we had today's computer technology, we could probably solve problems in minutes or hours that took us sometimes several days or even weeks to solve. The whole program could have been accomplished with a lot less sweat and a lot more ease, because we did everything we could do, but we were never absolutely certain that we were going to make it. And I had to repeat, the thing that I'm the most proud of, and I think we all are, is that with our entire McDonnell manned space effort there, we launched them, retrieved them safely without any type of injury to any of the astronauts, and that the whole program was accomplished with a minimum loss of life is still phenomenal.
And you mentioned the slide rule. If you've never had a chance to see a slide rule or play with a slide rule, you should. Some of us, even back in high school, got to do all of our chemistry and math equations using that slide rule. And talk a little bit, Bob, about just the nature of everything was drawn by hand, right? You didn't have computer-assisted drafting or anything like that.
And we had big rooms of drawing tables, and every mechanical device had to be put on vellum, because vellum was a plastic material that would not expand or contract with temperatures, and they actually would use those things to manufacture the parts, so they had to stay pretty stable. So we had rooms full of those guys, and in today's technology, they do that on a computer and a 3D device. And also, we had to build a mock-up and take those pieces of equipment and stick it in there and put all the wiring in before we actually designed the permanent system of wires. And of course, that took a lot of time also. So it was time-consuming to do that.
So the idea of how we simulate things today would not have been possible back then. You're actually putting everything together and making sure it would work. A follow-up question that comes from Elkins, and Jerry will come back to you in a minute. Okay. Let me go to, I'm going to hopefully pronounce this correct. Is it Tan May? Tan May, let's go to your question as well, back in Missouri City.
My question is, what were some key difficulties faced by the team while building the first capsule for the Gemini project regarding the time period and the limited technology?
So can you think of some examples now? And Jerry, I'll let you start, then we'll go to some others. Can you think of an example of like, this was really a barrier for us?
Oh, well, of course, in our case, it was the size of the memory of the guidance system computer. We originally thought that we could put the entire program in there for each phase of the mission. The launch phase, for instance, the computer didn't have much to do as far as our vehicle was concerned, but it was the backup guidance system for the Titan. But each phase of the mission there turned out the software program was enormous relative to the size of our memory capability, and so we had to develop an auxiliary tape unit, and this literally had real tapes there, and as they would complete a phase of the mission, go to the next one, why that reel would start up and load another program. It'd wipe out totally. The program was in there, and get another one for the next phase. Wow. And this went on and on and on. And there were I don't know, 6. There turned out to be I think 7 or 8. There, no, 9. These programs were you kids might be familiar. They were not Fortran or Kabul or any of that. They were machine language, and so each mission had its own specific set of software programs there, and it turned out to be we could use some portions were duplicated, but there turned out to be 9 different particular segments there out of 10 missions. Wow.
So much more time taken. I want to go here now as well. So take it away, Phoenix.
What was NASA's hiring practice with respect to meteorites and gender during the Gemini mission phase, and what kind of positions did they fill, if any?
That's a great question. She's asking about, again, going back to that time on a non-technology perspective, women and minority hiring. Did you get to work with, were there women engineers, Earl?
Yes, there were.
Sure.
I don't remember exactly how many, but guess is on the Mercury and Gemini programs, probably 10 or 12 women in engineering. Obviously, there were women in other activities. 3 or 4 of the engineers that were women were the design type, working on the drawing boards, just like I was. Mm-hmm. And there were a couple of ladies that were, one was a thermodynamicist, expert in heating and cooling and all that stuff, and another one I can't remember where it was.
But this was true of the time period. I mean, there would have been far fewer women, obviously, in engineering classes in college than guys, I'm assuming. It would have, Norm?
Yeah, I think in our engineering class, electrical engineering, we had one young lady, but it was predominantly men. And in our...
One lady, Bob says in here. I'll invite Amelie to join us at the microphone as well, because she's going to take us also in terms of the time period, but on a slightly different tack. Go right ahead.
Okay. Do you think that public paranoia was the driving force in moving the space program from Mercury to Gemini missions? Why or why not?
Let's talk a little bit about the whole space race with the Soviets. The question deals with public paranoia. Do you think that was a driving force? Ray, give the students some idea. Were you really worried that the Soviets were so far ahead? Were you in there to fight to win, to beat the Soviets at their own game? What was that like?
It was very disturbing, but we had the smarts to say we can do this, and we proved it beyond a shadow of a doubt. And I mean, it was long hours, lots of time put in to figure out what we were going to do.
But at the time of the Gemini mission and certainly the Mercury mission, Dean, we were behind the Soviets, right? They were ahead of us?
Quite a ways behind. I think there were estimates at the time at least 18 months behind the Soviets. And of course, they launched Sputnik and Sputnik 2 ahead of us. We responded a couple months later with the Explorer 1, I think, that discovered the Van Allen belts. But we were behind. And the biggest difference, I think, what allowed them to get ahead of us was their launch capability. They could launch much heavier spacecraft than we could. But we were behind. And the media let us know that every day. There was no support from the media at that time. We caught up, we think, most people think we caught up with the Soviets about Gemini 5.
Okay.
I think we surpassed them at that time.
One of the things that really started the space race when they started talking about putting man into space was a concern that Russia was going to put a manned orbiting bomber. And so that made the race very significant. We had to get that done first, and we even worked on some of those things. But that was a time period when NASA became in existence, and it was bound and determined that only man in space would be involved with NASA, and the military was taken out of space.
Okay.
Nikita Khrushchev laid down a challenge to us to have a shoot-off with our ICBMs to see which one could go the furthest and be the most accurate. I mean, it was very serious.
Well, let's talk about those ICBMs as we begin to talk about your launch vehicles, because one of the things the students may not understand is that what you were doing to a large extent in the program was taking things that already existed and modifying them for the uses that you were after, and that was certainly true of the launch vehicles. We've got some still images we can bring up of Gemini 3 launching, Gemini 5 launching, and you seeing the launch pad. And as we do this, who would like to speak to the launch vehicle itself? What is this Titan II missile like, and what was it capable of doing?
Well, let's see. I've forgotten the exact fuel that it used, but it was totally different than the Atlas and had about 450,000 pound thrust. Our vehicle actual load, I believe, Earl, didn't you say about 8,000 pound? That's what we could put in orbit. There's a lot of difference between what you can lift and what you can put in orbit. The Titan was an intercontinental ballistic missile, and we literally took the nuclear warhead off and put the Gemini on it, as we did with the Atlas there. But I cannot for the life of me think of the fuel.
Well, let's go to two questions from Elkins High School, because they're going to ask us to get into this a little bit more. Robert, we'll go to your question first, and then once you've asked it, we'll hear Carlos's, and then we'll deal with both of them. So, Robert, take it away.
Did the requirement of using an existing launch vehicle make the project more or less difficult?
So Robert's question is the requirement for using an existing launch vehicle. Did that make the project more or less difficult? And Carlos, your question about launch vehicle, go right ahead.
All right. What were the most difficult modifications required on the Titan II to launch the Gemini spacecraft?
And then he wants to go further and ask about modifications to the Titan II. What were the most difficult modifications to the missile to make sure that it all worked well? So, Dean, you want to talk a little bit about either or both of those?
In my opinion, having to work with an existing launch vehicle was to our advantage. There were a big, long development for any launch vehicle, and I think it was like 20 or 25 launches prior to the time that we figured it was ready to be man-rated. And with regard to the man rating for the missile, there are a lot of electrical redundancy things that had to be incorporated. As I recall, there was also a system that monitored the well-being of the launch vehicle, and that was piped into the spacecraft so that the astronauts would have an idea if they were on a nominal flight or something that was non-nominal. So those were some of the things that I recall that had to be done with the launch vehicle itself.
Well, I'll go to you.
Okay.
Since you're on my right, I'll go to you first. Earl.
With a man-rated situation, part of the activity and priority that had to be the fix of it had a pogo situation. The pogo means vertical oscillations, and
okay, so let's stop there for just a minute, because some of us may not know vertical oscillation from a horizontal oscillation. So we're talking about something that's going up and down,
yes.
And that's a bad thing. You're telling me, Earl, you didn't want it to happen.
That's right.
And because if it did happen, what would happen potentially?
Well, if it happened and got larger or in volume, it would affect the astronaut, your passenger.
Okay, and he would feel the shake too?
Yeah.
Okay, make it difficult perhaps for, okay. Yes, go ahead, Dean.
I think the pogo that they measured, one of the maximum pogo was something like 2.5 Gs. Now that's quite a bit of force, quite a bit of energy. And I think the NASA requirement was something like 0.1 G pogo. So they had to reduce that to get it down to the point where they thought the astronauts could withstand it and be comfortable with it.
Right, because they've got those G-forces are acting on their body, obviously, as the launch is happening. Let's look at some images.
In addition to the launch G-forces.
Right.
Yeah.
Let's look at some images. We've got a picture of mating the Gemini capsule to the launch vehicle, and then we're going to have some video that we can run next of going up in the launch pad and getting into the capsule so you guys can get a sense of its height and that thing. And as we look at this, Ray, let's talk about this a little bit as we look at the video of going up in the launch pad and getting into the capsule. Talk a little bit about, you and Norm can speak to this, I'm sure, about the cabling and the connections and how high are we dealing with as we look at this video. What's there?
Well, it was all 285 foot to the top of the gantry. All right, to get in the spacecraft, you had to be up on that pedestal. Well, it was very hard to make sure that everything was going to work whenever they crawled in that spacecraft. But as far as the vertical and pogo thing was, that was strictly the Titan missile. And all they had to do with that was damp it down so that they wouldn't have no problems whenever they went in launch. But it was a very trying time whenever they turned that loose.
You see that, guys? They're on an elevator that you can see out. We're always on the outside of things going up 200 feet. And a lot of folks wouldn't want to ride an elevator like that.
So they go up to the top. The astronauts, these are images, obviously, of actual Gemini astronauts getting into the capsule. Talk about the process of putting them in the capsule and making sure all of that was good to go.
Well, there was a procedure written to put them in the spacecraft, and Gunter Wendt was the guy that read it off. There was 3 technicians that had to put them in the spacecraft. Well, you don't see me, but I was behind Gunter Wendt with the same thing, reading it, making sure that he read everything exactly right.
And this process takes about how long to get them into the capsule? We're talking minutes, hours?
Oh no,
it was a long process.
It was a lot longer process than that.
And then they're locked in, kind of like sardines in a can,
right,
with not much more space than that. And then they're just going to sit and wait for a while. And Norm, we've got some questions about the communication system, so we're going to start to talk about that, because at this point now, the astronauts are sitting on top of that thing, hopefully waiting to go up into space quite successfully. Let's go to Joel back in Missouri City, Texas at Elkins High School. Joel, what's your question about communications?
What were the most important breakthroughs in communication systems that came from Project Gemini?
So what important breakthroughs existed in communication? So let's talk a little bit, Norman, about what was the communication system like. So the astronauts were obviously able in the craft to communicate with people down on the ground, and all of that was through analog wire going down and through.
Yeah,
right? There was no digital.
They were through what was called the umbilical, which was attached to the spacecraft until just a few seconds before launch. And so we had that land communications, but we also could broadcast through our UHF and HF links to the various test sites and things.
So we've got some video of the ground control network, the ground tracking network that we can bring up as you talk about this and how you were able to follow them along. So continue, Norman.
Right. The radar beacons were used by the ground tracking sites to precisely locate where the vehicle was. And there were tracking stations around the world, so the satellite was never, or the capsule was never very few minutes out of some site. We also had command receivers in there, so the ground could command things to happen if the astronaut was not able to do it, or some reason for him not being able to do it. And there was telemetry transmitters in there so that the doctors and engineers on the ground could tell the status of the astronauts and the different systems on the capsule.
And that ground tracking network you see in this video had to be built. Various places around the world where radar stations could be set up, because obviously we're not talking about today's era where there's all sorts of communication satellites in space. There were a few satellites up in space by this point in time, but not too many, right, gentlemen?
No.
Not communication satellites?
No,
Telstar wasn't up yet and that kind of thing?
There were no communication
satellites. So all of that's
at that
happening
time.
from radar on the ground. So you get that kind of sense. We're going to go to some video now which will show you liftoff, all the way to the first stage separation of the craft, so you get a sense of what that was like. And with this liftoff to stage separation, let's go ahead and listen to the audio as well, so you can hear the countdown and see what's happening and get a sense of what this thrust is like that Earl was going to lift him up with, hopefully successfully.
6, 5, 4, 3, 2, 1. Ignition. Lift off.
And that what we saw at the end of that was the stage separation. So the missile, in essence, had different stages, so it could thrust and boost it up so far, and then that would fall away, and then some other stage would take it a little bit further.
right.
Am I remembering all that right?
Yeah.
There was a two-stage system.
This was.
Okay.
Yeah, Titan was.
Titan was a two-stage system. So there you get a sense of it going up and that kind of thing. And talk a little bit about what was happening on the ground, gentlemen, and that communication process. We got some great pictures that you provided about being inside the blockhouse. So let's go to those inside the blockhouse images, which existed there at Cape Canaveral. What's happening on the ground as the astronauts are getting into the vehicle and you're going through the checking and everything? What was that process like?
Well, for the guidance system, it was to, you had to, that's me.
Ah,
Be darned.
you're right there with the headphones on and the plaid shirt?
The next one to the right.
Then, Jerry, you look exactly the same.
I haven't aged a bit.
Not a bit,
That's
not a
me.
bit.
Anyway, on that panel, there I was orienting the guidance system. We had 3 accelerometers and 3 gyros on a platform that at liftoff basically you had to point it toward the center of the Earth. That was our orientation. The computer pre-launch system or the pre-launch software was all self-check. It would do its own. It would, in addition, it would do some reality checks, if you will, on the inertial measuring unit, and it would even fire up the horizon sensor, and a lot of it was automated. Our job was to get it started, monitored as it went through. It never, ever went through correctly. And so you then to find out what was wrong and correct that and do it again and do it again and prepare it so that you actually, I mean, every one of us did there. I gave a go for the guidance system, and Norm gave it for the command, for the computer system. Each guy certified that his system was in a launch configuration and was safe to go.
And you may not be aware of this, but more than one launch was held. More than one launch was obviously aborted because of any number of reasons, weather, postponed, that kind of thing. You had to make sure that everything was good to go. We had one final question that actually came to us through email, and Norm or Ray, I'll let one of you speak to this, because they're saying, with today's communication systems, what makes the launches different today than what you guys had to deal with?
Well, one thing is you do have satellite communications now, so that's a completely different atmosphere than depending on tracking stations on the ground. But when you've got the vehicle sitting there on the pad like that, I suspect the things are somewhat the same. You're still talking to the astronauts as they're preparing for launch. And, of course, once that umbilical leaves, then they're strictly on communications links.
So that gives you some idea about the technology of the time, what kind of ship they were going up in, so to speak, the missile that was being launched. Now let's talk about what was on top of that missile, the capsule itself, and what they were oriented to do in these missions. Why does Gemini really matter for the Apollo space program? What were they trying to prove to make sure that they could do so they could get man to space and back? We've got some images we can bring up now of the spacecraft drawing, the spacecraft and the command module. And Earl, we have the space capsule where the astronauts are sitting, but there's also some sort of adapter or what was the backside part of it?
Yes, the backside part, which is the white part in the mission, is in the picture is the adapter.
Okay, and it's holding equipment or what?
It's holding equipment. It's holding fuel. It's holding hydrogen and oxygen. It's holding, in some cases, fuel cells, batteries. All that kind of stuff.
Everything you could stuff in there so that the astronauts had a little bit more space to work with?
That's correct.
And there you see the command module on one side and then the adapter in the back side as well. And this was not true of Mercury, right? This was a change from Mercury.
Yes, it is a drastic change from Mercury.
And just to give you a sense of size and scale, everybody, here are the engineers or people working on the capsule, and you're going to see some astronauts by the capsule so you get a sense of just how small it was and fitting down in there, that kind of thing. And then we've got some video that we can run in a moment, too, about building the Gemini capsule. And as we begin to do that, I want to go to Carlotta. You had a question about materials as well. Go right ahead.
How were the materials necessary for construction of the spacecraft determined, and what were the safeguards against micrometeorite bombardment of the craft and astronauts outside of the protective envelope of Earth's atmosphere, especially during EVA?
So we want to know where the materials come from, and in essence, did you have to manufacture or modify materials, do all sorts of different things to make it all work? Bob? Oh, you want to talk a little bit about that?
No.
You want Earl to? Earl, you get to talk about it. See, I like these moments in time. No, I don't want to talk about that. Earl?
Okay, with respect to the capsule part, the materials were titanium. That was it's a mixture of 60% aluminum, 40% Inconel. Okay, that was used for the inner part of the capsule, the pressurized section, the walls and the two bulkheads. The other materials concerning the structure was made of the shingles, and Rene 41. I'm sorry.
No, don't worry.
41.
The Rene 41 is really interesting to me because that's a material that actually didn't exist prior to the space program. Am I remembering that right?
No, that's correct. That was a specially developed thing. And that was the material used for the outer skin, which also we call the shingles. Okay. With regard to the structure and the adapter section, we got a little wild there. We started using a special alloy for the stringers. It was a stringer and a bulkhead type structure, just like on airplanes. And the stringers, which carry all the load, is an extrusion made of a magnesium alloy. And the reason for that is that the magnesium was the lightest material to get the strength that we needed. And we really need to have that down to as far as we can to make it work. And that structure, composed of magnesium and aluminum alloys mixed, was the bad part of it was taking a risk because magnesium touching anything starts corrosion pretty well. So we had to develop sealing techniques on those two materials to make them work right.
So you were constantly working with new materials or thinking about using materials in different ways than you had before, because obviously you were asking something to operate in an environment that was very different from what would be here on Earth.
Yes.
So you get some more pictures, astronauts in the capsule, again, the size of the capsule. And obviously one of the major parts of the mission of the Gemini project was to see if we could indeed get people to stay in space long enough and successfully enough that they could go to the moon and back, which was going to be about a 7-day to 10-day experience anyway. So long duration space flight was important. All the Mercury missions had been really quick, short, very to the point. So we've got a couple of questions coming to us from Missouri City that deal with that as we talk about the long duration space flight, and then we're going to go into spacewalks and the docking, the rendezvous work, which is really kind of cool. So Missouri City, we'll go down to Adesh. I hope I'm pronouncing that correctly. Go right ahead with your question.
How did the engineers simulate realistic conditions while testing things such as life support?
So that's one question about making, how did you simulate realistic conditions when testing things such as life support? And Tanmay, I'll have you just ask your question as well right now, and we'll deal with them both kind of together.
What were some of the experiments planned to be performed in space, and what information was gathered from these experiments?
So we've got a couple of questions. One was about simulating the conditions, and then what did you actually want them to do up in space to make sure you knew that long-duration spaceflight was possible and that kind of thing. So what did you do to simulate realistic conditions? Talk a little bit about that. Norm?
Well, here in St. Louis, we built a vacuum chamber where we could put the entire Gemini spacecraft with its adapter in that chamber, put the astronauts in their spacesuits and go in there and evacuate that chamber down to a near space condition and run the heat and the vibration and so forth. So we simulated pretty close here in St. Louis what it was going to be like for them. And so there were tests like this at just about every facet of the program.
Yeah, each spacecraft went through that test prior to shipping it to Florida.
Weightlessness is the only thing we couldn't duplicate.
Yeah.
And obviously there were experiments that were, they did things weightless. There was some weightlessness training because you did some things underwater so they could simulate some sense of weightlessness. And then the parabolic flights.
That's seconds.
Right.
30 seconds to 4 minutes is max.
Right, and so I don't know if you know, that's the way they also filmed the film Apollo 13 when they wanted to simulate weightlessness. They did the parabolic flights and they filmed it, but you're literally just weightless for just a couple minutes maximum.
Yes.
And so you've got to be very precise in what you're practicing. I'm going to practice eating from my food packet in this minute up in weightless environment, and then for the next flight I'm going to, practice opening up this can of whatever that I'm going to have to, some tool I'm going to have to use. So we've got some video we can show, which we've called long duration spaceflight experiments. It won't have any audio, but we can get some nice visuals of space and what they were doing with the Gemini mission. As we begin to answer the question that Tanmay asked about the experiments planned, what were they really looking for? What was it so important about being able to make sure an astronaut could last 10 days, 2 weeks, that kind of thing? Dean?
Well, when you talk about experiments, you're talking about those things that the astronaut had to do.
Correct, exactly.
Well, they went through all sorts of training for that. They were trained in what do you call them, the centrifuge and those kinds that would simulate launch. But with regard to long-term weightlessness, that was pretty much impossible to do on Earth. And they went through, for EVA, they went through the neutral buoyancy things with the underwater, trying to work out the processes and procedures for work in space, but we couldn't ever simulate the long duration weightlessness thing. One thing that they did do, of course, was make sure that the couches for the astronauts were very, very comfortable, and they did provide exercise bungee cord kinds of exercise things that they could use in space to keep muscles from atrophying, that sort of thing.
So they're going to be up there for a period of time, and they're going to have to do some unique things. And one of them is they're going to change orbit. They're actually going to be able to control the orbit and the manipulation of the capsule in a way they couldn't during the Mercury missions, because obviously they've got to take their capsule and train for docking with the vehicle. and rendezvousing with vehicles, two important things that would make a big difference in the Apollo missions. So let's begin to talk about this orbital change work as we look at some images where we can look at the maneuvering controls and we can look at the thrusters and those kinds of things. And Bob, talk about the importance of this. Why does this matter now that we can actually manipulate the capsule in this way, and how's that going to affect hopefully figuring out what we could do with Apollo and going to the moon?
Well, that was the only way we were going to get back from the moon. That set of pictures there shows the various kinds of the RCS system and the orbital maneuvering system. The orbital maneuvering system had thrusters that could change the translation, the vertical translation, and the horizontal translation. And then the RCS system, which was up on the front of the cylindrical part and the very front part, was the same as Mercury, and that was called the RCS system, and that would control pitch, roll, and yaw. So those are called 6 degrees of freedom of anything that's in motion. So that allowed them then to get into the same orbit with another vehicle, and then we proved in Gemini that we could do that and put them together. Getting back from the moon required launching a lunar module that was now out of oxygen, and so you now got to get back to the good old Earth, and so they would fire a rocket off and get in the same orbit that the Apollo was orbiting the moon, waiting for them to come back with one astronaut, and then they would dock, the two astronauts would get out, get in the Apollo, and jettison the lunar module back to the moon. So that process that we developed in Gemini was very important to even go to the moon.
Well, the one of the things that the Gemini different vehicles that we tried to prove was when they first developed this rendezvous capability, they thought, okay, maybe we'll do it in 3 orbits, maybe even 4 orbits, and then they perfected it till they get down to 2 orbits, and the real jewel was when they could launch right to the second, such that they would be in the plane and come up and rendezvous on the first orbit. Then that's perfection. And we actually did that a couple of times.
Wow.
Yes.
When you think about that, that's exceptionally impressive.
Well, when I say we, that's the other 10,000 people plus us 6.
Okay.
Yeah.
You 6 alone. I understand. You 6 alone weren't doing it. We've got some video we can show of astronauts docking in space. Again, we'll play the video without sound so you can just see as it happens. And pick up with this conversation, Bob, about docking the two crafts together, because this has to happen, obviously, if you're going to go to the moon and back. And what did you have to do to make that successful?
So we ran a test at the altitude chamber room and put a Gemini and a target docking adapter out there and adjusted the 28 volts going to the light bulbs until the astronauts were happy it was bright enough.
I want to talk about those light bulbs for just a minute. We'll bring up another video, which I actually called Narrated Docking in Space, but we won't have to hear the narration because I want Bob to give the story about the light bulbs as you come up. Remember this, folks. You're in space. There is no light. Very dark, and now you've got to make sure you connect to this other vehicle. So they're going to put lights on this other vehicle so that you can see where it is as you come toward it. So think about being in an entirely darkened room and then all of a sudden someone turns the lights on. What do your eyes do? How long does it take you to adjust? What you're about to tell us, Bob, is the process you had to go through with the astronauts so they could deal with this, right?
Right. We took a Gemini and a target docking adapter, and there was a big room in front of the altitude chamber where we had to do some testing and all kinds of mechanical devices to get that thing in the altitude chamber.
But you see lights there.
See, the lights are on the very front of it. They were signal lights. Lots of times when we throw a switch, a light would come on and tell you some function behind that had worked. So we got it black as we could get it, and I had a rheostat that I could adjust the 28 volts on each of the lights. And I adjusted it down to 7 volts, and that's when the astronauts decided that was bright enough.
Wow. And Earl, you wanted to add something?
Just a quickie. Those pictures there of the docking and the rendezvous, that indicates to me that is when we caught up with the Russians.
Yeah. Well, another thing is you asked about testing. We built a huge wooden platform down at on Kennedy Space Center, and we actually put the Agena and the Gemini spacecraft up there.
And in case you don't know, the Agena was that vehicle that they were rendezvousing with in space.
Right. And we needed to know that everything was compatible electronically wise. We didn't have any what we call EMF between the two. We didn't have any noise factors. We could actually bring those two vehicles together because we had a radar on the nose of the Gemini, and then the transponder was in that target docking adapter. And we had to know that those worked, that the latches worked and everything. And we actually, that was a mammoth test. Put that whole vehicle up there. And the reason we went on a wooden tower was to isolate it from the Earth as best we could as far as putting it into a free space RF environment.
Wow.
That was an awesome test.
And obviously helpful. So we're docking in space, we're going to maneuver spacecraft in space, we've got to be able to change the orbit in space, all those things that would be essential to the moon. We've also got to walk in space. And so we need to talk about these extravehicular activities a little bit so you can see that. We've got some beautiful still images we can show you of spacewalks as we do this, and then we've also got some video we can run for you entitled Spacewalk without any sound so you can see this. So we had the question before about micrometeorite bombardment and making sure the astronauts were safe as they... What kind of preparations were made, Earl, in the design of the capsule that were designed to hopefully help facilitate a spacewalk? Were there like handholds on the side and that kind of thing?
Yes, we created handholds, Norman, and we worked on other methods of having the astronaut grab onto something as he went back, say, in the adapter to perform an experiment. We use Velcro.
Oh, really?
Yeah, we use Velcro pads. That was tried out, and although it was a good way for a structural guy to think, it was a little bit too tough. The astronauts didn't like it. So we got off the Velcro pads and continued working with putting handholds and handrails and things like that.
And even though they had practiced underwater, these spacewalks were not easy things. You learned all sorts of things that you weren't expecting.
Oh gosh, the first one, Ed White's, there was he was only out for I think about 20 minutes, but he had difficulty getting out. He had a lot of difficulty getting back to the adapter so he could get his maneuvering unit. He was just totally fagged out before he got back in. When he got up to I think it was Cernan, he really had a tough time of it. But they finally a combination of the in-flight experience plus the water testing, the buoyancy trainer, they worked it out, and by was it 9? I guess it was just smooth. They had no problems at all with that. 12. Okay.
On the later walks, there were some scientists from all around the world. I remember we installed a little rectangular platform on a door, and they had a bunch of sensors in there that were going to collect the particles that would be traveling through space as they're going around in orbit. And so the astronaut that went out had to open the door on that thing as he went out to do his thing, and then he would go in the back in the aft part and do all the things he had to do. And when he came back, he had to close that thing, because that came back with the reentry part of the vehicle. And so then they got the little box at the end of the mission and went back and decided what got left in the box.
Wow. And Norman, in terms of communications, are there wires going out through those umbilical cords?
Yes, there were.
Is that how it was?
Yes.
So the reason I'm hearing, because I'm hearing NASA talk to the astronaut and the astronaut speaking back, is because there are wires going out in that cord that are somehow connected back to the capsule and it's being sent.
Right. He's still using the capsule communication system just through his umbilical. There's that wire that goes out and plugs into him.
My gosh.
Yeah.
And were the EVAs important Obviously, one, to see if we could work out in space if we needed to repair any kind of craft on a long mission. Did the EVAs also help just in terms of thinking about when we walk in on the moon and we're doing stuff?
Oh, yes.
Was that a big part of it as well, Dean?
Big part.
That's what they were. They were EVA on the moon.
Yes.
Right.
Yeah.
And so the idea was, what kind of equipment can I be wearing to perhaps move this way or do what I needed to do or grab objects?
After a long term, the exercise and the body perspiration and the fogging of the visor, everything were problems that had to be uncovered and then solved, because once he got to the moon, that was it. Everything had to work.
Yes, because once you're up there, you're on your own to
You're
a
on
large
your
extent.
own.
Even if I'm in communication with Norm back on the ground, I'm still really on my own. Earl?
Let's not forget the first EVA where White went out, and he had with him a maneuvering unit, a gas-powered maneuvering unit.
Little air gun.
Yeah. Which was quickly invented.
Yes.
And it seemed to work pretty well.
And that helped him just shift where he was?
Yeah.
Yes.
Oh, wow.
And,
He's on a tether.
Right.
He had so much fun with that they had to beg and command he comes back in. He wanted to stay out there forever.
It was like a paint spray gun is what it looked like, but it had compressed air
it was compression, oxygen coming right out of the umbilical cord.
And
over to that.
And so when that air came out, it pushed him a certain direction. He could use it to maneuver himself.
It went out to thin rods, cylindrical rods, and the air went out this way, so it gave him some thrust there, a little bit external to him, so that could move him back straight.
These Gemini missions begin. We get to in 65. We're on the moon, July of 1969, 4 years later, and we're getting those people back. Think about the amazing amount of change, success that happened in the course of this short decade of time, and the fact that these 6 men were just part of making all that happen. Gentlemen, I can't thank you enough for joining us today. Talk about problem-solving extraordinaire. A passion for your work and doing it. We thank you for that and for giving the students a chance to understand what it would be like to be an engineer in that time period or just go through the engineering process on any project you're involved with. So thank you very much for joining us today. Thank you all for joining us as well via the web, television, and of course, a big thanks to our folks down at Elkins High School in Missouri City, Texas.